Okay, welcome to chapter 4. In this chapter, we're going to be looking at mainly Ohm's law. This is relatively a short chapter. We're going to be covering sections 2, 4, 5, and 6. But the main focus is going to be on Ohm's law, power, and energy. So now that we already know what voltage is, we already know what current is, and we know the effect of resistance, we can put all that together into one very important law that is called Ohm's law. And this is the equation that represents that law. It basically says, and the best way to describe it is using equation 4.3, it basically says that the voltage is proportional to the amount of current, and the constant of proportionality is the resistance. Or basically saying is that the voltage is equal to the resistance times the current. So based on this equation, you can then solve for current if it's needed, like in equation 4.2, or for resistance, like in equation 4.4. But the important thing to notice is that all those three elements, all those three parameters are related, very closely related. If the voltage increases, as you can see in this expression, is going to be due to the increase in current or due to the increase in resistance. And as we already know, resistance and current are inversely proportional. So the least the amount of resistance, the more current you're going to have. And you can see that in here, right? So this brings everything into one place. Current is equal to the potential difference over the resistance. If the units of voltage are volts and the units of current are amps, and the units of resistance are ohms, then everything is going to be in place. So in other words, if you divide volts over ohms, you're going to get amps. If you multiply amps times ohms, you're going to get volts. And if you divide volts over amps, you're going to get ohms. And again, in this book, they use E to represent voltage, but E is used more to represent a source. But I like to use V for voltage, for anything that's related to voltage, but you can also use E, so don't be surprised that they use capital E for that. Okay. So, for example, given in this figure, right, that you have a resistance and you have two points connected to the resistance. In the first case, you have a positive connected on the left-hand side, the positive of the voltage source, and the negative connected on the right-hand side. And based on our concept of voltage and conventional current flow, then we can tell that the current is flowing from left to right towards the least potential. Okay, that's really very important because the polarity here tells you the direction where the current is flowing. In the same way, if you look at figure B, from figure B, the polarities are reversed. So if the polarities are reversed, then the current direction is going to be reversed. Because remember, conventional current flow always flows from positive towards negative. From positive towards negative. That's really, really important. So let's see something here. It's really very important that that this figure is really clear as far as the polarities and as far as the direction of the current flow, and also as far as understanding Ohm's law. So for example, in this example, you have example 4.1, you want to know the current due to applying 9 volts up to a resistance of 2.2 ohms. So it will be this case here. You have 9 volts across the resistance, and the resistance is 2.2 ohms. So if we do that, okay, and now we're going to look at the concept of power. Okay. is really an indication of how much work is the energy conversion can be accomplished for a specific amount of time. So power is very dependent on time. It's the amount of work over a period of time. The units of power are the watts, and we're going to use the letter W to represent watts.